K-fold cross-validation is a method used to evaluate machine learning models by dividing the dataset into multiple parts, or folds. Here's a simple explanation tailored for management. K-fold AI/ML architecture. Model architect, Pradeep K. Suri. What is K-fold cross-validation? K-fold cross-validation splits the dataset into 5 parts, as specified by n_splits equals 5. For each iteration, the model trains on 4 parts and evaluates on the remaining 1 part. This process is repeated for all 5 parts, ensuring that every part of the dataset is used for validation exactly once. Steps. 1. Data splitting. The dataset is divided into 5 equal parts, folds. In each round, 4 folds are used for training, and 1 fold is used for validation. 2. Training. The model is trained on the training data, which consists of 4 out of the 5 folds. 3. Validation. After training, the model is evaluated on the validation data, the 1 remaining fold. This helps in measuring the model's performance on unseen data. 4. Repetition. The process repeats 5 times, with each fold being used for validation once. Purpose. Comprehensive evaluation. K-fold ensures that the model is evaluated on different segments of the dataset, providing a more reliable performance measure. Avoiding overfitting. By testing on different parts of the data, it reduces the risk of overfitting, where a model performs well on the training data but poorly on new data. Summary for management. This approach allows us to test the model thoroughly by rotating the training and validation data, ensuring a well-rounded performance evaluation. It helps in building robust models that generalize well to new data. This code snippet demonstrates the use of K-fold cross-validation in machine learning, specifically for splitting data into training and validation sets multiple times. Here's a detailed breakdown of the process for an AI/ML architect. 1. K-fold initialization. The K-fold class from sklearn.model_selection is used to divide the dataset into n_splits, 5 in this case, for cross-validation. The parameter shuffle equals true ensures that the data is shuffled before splitting to prevent any order-based bias. 2. Splitting data. Kf.split, x, generates indices for splitting the dataset x into training and validation sets. Each iteration of the for loop creates a unique combination of training and validation data. In each fold, 1 portion is reserved for validation, and the remaining 4 portions are used for training. 3. Training and validation sets. Train_index and val_index are the indices generated by K-fold. Using these indices, the dataset is split into x_train, training features, x_val, validation features, y_train, training labels, y_val, validation labels. 4. Model training. The model is trained on x_train and y_train for 10 epochs with a batch size of 32. This process is repeated for each fold of the cross-validation. 5. Model evaluation. After training on each fold, the model is evaluated on the corresponding validation set x_val and y_val. This helps to assess the model's performance on unseen data. 6. Cross-validation process. The entire process repeats for all 5 folds, ensuring that each part of the data is used for both training and validation. This reduces the risk of overfitting and provides a more generalized model evaluation. By utilizing K-fold, the model's performance is averaged across multiple splits, leading to a more reliable estimate of how well the model will perform on unseen data in real-world scenarios. In K-fold cross-validation, the typical metrics used to evaluate model performance are root mean squared error, RMSE, and R-squared, R superscript 2, especially for regression tasks. Here's how these metrics are used. 1. Root mean squared error, RMSE. RMSE measures the average magnitude of errors between the predicted and actual values. It penalizes larger errors more than smaller ones due to the squaring of differences. Formula. RMSE equals 1 n sigma I equals 1 n, y caret I, 2 RMSE equals \sqrt \frac 1 n \sum_I equals 1 caret n, y_I, \hat y_I, caret 2 RMSE equals n1 I equals 1 sigma n, y caret I, 2. Where y underscore I equals actual value. Y caret I backslash hat y underscore e caret I equals predicted value. NNN equals number of observations. Lower RMSE indicates better model performance, as it shows that the prediction errors are smaller on average. During k-fold cross-validation, RMSE is computed for each fold and then averaged across all folds to give an overall performance estimate. 2R squared, R superscript 2. R superscript 2 represents the proportion of the variance in the dependent variable that is predictable from the independent variables. It indicates how well the model fits the data. Formula: R2 equals 1 sigma I equals 1 n, y caret I, 2 sigma I equals 1 n, y, 2 R caret 2 equals 1, backslash frac backslash sum underscore I equals 1 caret n, y underscore I, backslash hat y underscore I, caret 2 backslash sum underscore I equals 1 caret n, y underscore I, backslash bar y, caret 2 R2 equals 1 sigma I equals 1 n, y, 2 sigma I equals 1 n, y caret I, 2. Where y underscore I equals actual value. Y caret I backslash hat y underscore e caret I equals predicted value. Y backslash bar y equals mean of actual values. R superscript 2 values range from 0 to 1, where R superscript 2 equals 1, perfect fit, the model explains all the variance in the target variable. R superscript 2 close to 0, poor fit, the model does not explain much variance. In k-fold cross-validation, R superscript 2 is calculated for each fold, and the mean R superscript 2 across all folds gives a robust estimate of the model's predictive power. Using RMSE and R superscript 2 in k-fold cross-validation. Model evaluation is done on the validation set for each fold, calculating both RMSE and R superscript 2. After completing all k-folds, the average RMSE and average R superscript 2 across all folds are taken as final performance metrics. This process ensures that the model's performance is validated on different subsets of data, providing a more reliable assessment of its generalization ability. Thank you.